So we have this system that's being described here. So we can read about it. During matinee hours, moviegoers arrive at a theater according to an exponential inter-arrival time distribution with mean of 1.6 minutes, and the first arrival is at time 0. Most people, around 95%, directly approach the ticket sales counter, where they wait in a single line until one of 2 clerks is available to serve them. The time to purchase tickets follows an exponential distribution with a mean of 2.4 minutes. Upon completion of their check-in, they join the remaining 5% of people who pre-purchase their tickets online. From there, 30% of people walk directly to their respective theater wings, taking between 2 and 3 minutes uniformly distributed. The remaining 70% walk to the concession area to buy snacks, taking between 30 and 45 seconds uniformly distributed. They wait until one of 5 clerks is available to serve them, and the time in minutes it takes for them to order and receive their snacks follows a Weibull distribution with parameters beta, alpha. Snacks in hand, they walk to their respective wings, taking between 1 and 2 minutes. Run the simulation for 10 replications of 2 hours. How long are lines in the ticket sales and concession areas? How much time do people spend waiting? How much time do people spend in the lobby? What is the total time in system? Do you have any recommendations? What are they? So this one is a little more, this one it's just harder because it's got like a little bit more steps and stuff, some decide logic in it. So we can go and try to build this. So if you have the ability to watch what I'm doing and build at the same time, go ahead and do that. I know that it's hard with the screen. If you don't have dual monitors or if your screen is small, I know that can be tricky. So if you are not able to build it at the same time, you can just watch what I'm doing. I know it's not the same as doing it yourself, but at least you'll see what's happening. So we have matinee hours. Moviegoers arrive at the theater according to an exponential inter-arrival time. So we have basic process, create. We want to say that moviegoers arrive. Actually, I don't know if I'm allowed to use hyphens. I'll just move the space. And these are, let's call these customers. They arrive according to a random exponential distribution with a mean of 1.6 minutes. It doesn't say how many entities will per arrival. We're going to assume that everybody comes in one by one, even though in the real world we know that most people come in groups of 2 or more, right? I think very few people go to the movies by themselves. Those are brave people. I wouldn't go to a movie by myself. I'd feel weird. But okay, so we'll just say that each group is considered a single entity. So say, okay, so moviegoers arrive. Then most people go to the ticket sales counter where they wait in a single line. So now we're going to have a split in these people. So let's use a decide block, and we're going to decide by percentage, and we're going to say that 95% statistics. This is a question. 95% of the time, this is true. They're going to go to the ticket sales counter where they wait in a single line until one of 2 clerks is available. So this is a single line means a single process. We can define it once. And we can say this is the ticket sales counter. And we call this, we'll say this is a seize delay release. And we have clerks, right? Now, this is a very common mistake. People will say one of 2 clerks. So they'll put a 2 in here. But remember, in this area, we're defining the process. We're not defining the list of resources. So we're trying to see how many clerks does it take to run this process. So you only need one person to sell you a ticket. You don't need both of them, right? So the time to purchase the tickets follows an exponential distribution, which is not one of the built-in ones. So we'll go to expression. Let's make sure we change this into minutes. And we want to go to the expression builder. This is a random function. It's an exponential function, and it's got a mean of 2.4 minutes. As you're filling it out in the expression builder, it will put the arena expression down here. So if you already knew that this arena expression for an exponential distribution is expo, you could have just typed it out directly. But we have this, and we want to make sure we don't forget that we have 2 ticket clerks available. Okay. So then upon completion of their check-in, they join the remaining 5% of people who pre-purchased their tickets. From there, 30% of people walk directly to their respective theater wings, taking between 2 and 3 minutes. So this is now where it gets a little tricky. We have these 95% people rejoining the 5% people, but they're rejoining it to do what? Oh, there's something in the chat. Oh, the world without COVID. Yes, I know, right? Soon, guys, maybe 6 months. I mean, I know that's not soon, but we'll see how the vaccine goes around. Okay, so when we rejoin the 95%, immediately after that, if we read this carefully, we see that there's a second decision that's being made. So actually, from this ticket sales counter, we're going to have a second decide module, and I'll just put it down here. And this is now buy food. And we'll make this, what is it? 70%, right? And we want to connect this so that even the people that didn't buy tickets now still have to make they're going to buy food. The 30% are going to go straight to their respective wings. So let's put in a delay module. Delay. And we'll say this is walk straight to theater. And this is a transfer, or we can say this is a transfer. The delay time is between 2 and 3 minutes, uniformly distributed. So if you know the expression in Arena, you can go ahead and type it, or else you can right click, go to build expression. Again, this is a random distribution. It is uniform between 2 and 3 minutes. And so this is the Arena expression, unif 2, 3. Okay. And then they're going to walk straight to their theater, and they're going to exit the lobby. And at this point in this model, we're going to stop keeping track of them. So they're going to leave. Now the 70% of people that buy food, right? They go to the concession area. So first they have to go to the concession area. Oh, not this. So walk to concession. Am I spelling this correctly? Oh, and I forgot to change this. So this is going to be between 30 and 45 seconds. So I can type this out in one of 2 ways, right? Unif, I can go 0.5 to 0.75 minutes, or I can define it in terms of seconds, and it won't, like, you don't have to be consistent internally. So this is 30 to 45 seconds. This is 2 to 3 minutes. They walk to the concession area to buy snacks, and then they wait until one of 5 clerks is available to serve them. So It does not say that they're waiting in separate lines. So we're going to say that they're all going to wait in the same line. And this will be the concession counter. And this is going to be a seize, delay, release, because we're going to be using a resource and there's a queue. And we're going to use the, let's call this concession clerk. We only need one concession clerk to help a single person. And this takes a Weibull distribution. So let's go to expression, build expression, random distribution. It's a Weibull distribution with a beta of 7.78 and an alpha of 3.91. And if you have a question on what these parameters are, it's a little opaque, like it's not intuitive. Like when you look at a uniform distribution and the parameters are 2 and 3, you know that means that the lower limit is 2, the upper limit is 3. A Weibull distribution is a little bit complicated. You can go and look up the formula and see how these alpha and betas work in terms of how they relate to the mean and standard deviation. So let's just put this in, and this is in minutes. And we want to make sure that we have 5 clerks available. So there are 5 of them, right? And then snacks in hand, they walk to their respective wings, taking 1 to 2 minutes. So let's go. Let's add another delay here and say this is walk let's say from concession to here. And this is uniform 1, 2. Oh, 1, 2 minutes. We want to run the simulation for 2 hours. 2 hours. And we can look at the breakdown in minutes. Okay. And just should be fine to run. Let's take a look. Unconnected. Oh, I know what happens. I forgot to connect this. They exit the lobby. Okay, now let's try it. Run. I should have made these people. In fact, this is just for fun. I'm going to say that this is a picture of, not a report. Let's make this a person. Let's speed this up.
Sorry, can you do that again? Like how you pull up a picture of a person?
So I went to this entity, these people that are coming in, these entities, and I changed the picture. There's like a list of predefined pictures. You can also create your own. We'll go over how to do that later. But you can use.
Okay, I see. Thank you.
So in this 2 hours, we were able to serve 57 moviegoers. And we can take a look at the queues. And we can see that, well, actually, this is just one replication, right? So you can't really find out anything with just one replication. So if we want to look at some statistics, let's do 10 replications. And since we don't want to watch this animation for run 10 times, I'm going to turn off animation. So I'm going to say batch run, no animation. Let's hit stop and restart. Look at the status down here. Now, if we look at the report, we should have some pathways. There we go. So if we look at the waiting time, it looks like on average, people wait in the ticket sales for 1.5 minutes, with plus or minus 1. On average, at the ticket counter, they're here, and it looks like the most number of people waiting in. Let me make this big. It's hard to read. So you can see that we've got a minimum value, we've got a maximum value. We've got a min average, max average. So that is for each of the 10 replications, there's a minimum and a maximum. So this is now the average of all the minimums, average of all the maximums. The plus or minus is your margin of error for a 95% confidence interval. And then here are the numbers. So it looks like this is pretty good. I mean, on average, only one person waiting in line. Maybe we go and say, look at our concession clerks, man, they're only being used like, so they always adjust this. So it looks like it's a huge difference. It's actually not. It's they're idle about 40% of the time. These people are idle about 34% of the time. So it's pretty close. And on average, you can see that 3 out of 5 concession clerks are busy on average. You can look at the utilization rate, etc. And for the total time and system, the last question was, how much time do people spend at the lobby, i.e. what is the total time and system? We can look at the total time. On average, it's about 10 to 11 minutes, but we also have, some minimum, maximum averages, and then plus or minus. So any questions on this model? And I think I'll clip this and post this as a separate recording for the Lab 1 people, because we didn't have time to build this in Lab 1. Any questions on this?
How do you make a line that connects from one end to a between two processes or whatnot?
So there are a few different ways. If you don't have any, it's still in run mode. If you don't have these connections, you can go to this connect button, or you can go to where is it? Object connect, right? And just do it manually. The thing about doing this is each time you do a connection, that tool goes away. If you double click on this, you can do multiple connections without having to go back up to the toolbar, which can be annoying. So like if I want to make all these connections, if I were just clicking this once, I would have to go back up in each time. But if I double click, I can go do all of them simultaneously. And then there are a couple of things. One, if I bring in a new module and I put it on the line, it see how it's green? That's telling me that it's going to auto connect the 2 endpoints. So it's going to place this in between. And now this is connected properly.
Got it.
Yeah. And then the last, I think, little trick is if you have a module highlighted and you pull in a new module, it will connect it automatically. So those are all the little tips and tricks on how to do the connections.
Sorry, I have a question for the run setup menu, because there are multiple time units, so like this kind of confusing. Like, should we change them all to minutes?
No, you don't have to. So the base time units, this is just telling you when you read your report, is it going to show you in minutes or in hours, or whatever. And so this just depends. Like all of these processes were defined in minutes. So I don't know about you, but like when I see something like, oh, on average it's 0.002 hours, I don't have any conceptual idea of how long that is. Oh,
What
Benji.
about the time units on the right?
Now the replication length, this is the length of the simulation. And then warm-up period, this is something that we won't worry about, but in some systems, right? Especially when you know that like at the end of the day, all of the pieces that are works in progress are going to stay where they are. So you don't clear, like you want to have a warm-up period so that the pipeline is full, right? So you have like, all of the people are there. And then you want to collect the statistics once everybody, once there are parts throughout the system. I don't know if that was a very good explanation. But basically the warm-up period is where you're not collecting statistics. So this is at the start of the simulation, there could be a period of time where you're not collecting statistics. This is how long you're going to be observing. And then hours per day, this is like if you wanted to do, you have an 8-hour shift. So you could say there are 8 hours per day, so that every 8 hours it considers it a new day. Any other questions?